Welcome. First of all, thanks for attending this talk. Let me introduce myself. My name is Uğur. I'm working at Dell, and I'm part of the Office of Store CTO. So I have been looking at AI workloads for the last year, started with training. Now, obviously, a lot of stuff happening in the inference, and that's what I have been spending my time. Okay, so we're gonna talk about inference today and KV cache offloading. There are like amazing talks during the morning session. I'm sure some of you attended those. So as you know, like LLMs, inference are everywhere, right? Like every day probably you are like using the chat box, asking questions, right? And what we see is we see a huge increase at the model sizes, right? Right now we have billions parameters of model, like we see like extend on the context windows, right? The latest model have 1 million, 10 million context lengths. And also like the users like us, right? So they expect real-time responses, right? And all these trends are pushing the boundaries of existing infrastructure, driving up operational costs. And the KV cache offloading, you know, here comes and play an important role. So it's a niche, but increasingly important optimization for inference workloads. And with these techniques, the inference performance is improved significantly. So today during the talk, I'm going to talk about like how the KV cache works, what is the KV cache, why we need it, what are the storage requirements of KV cache from capacity and also performance perspective, what are the current stacks, and I'm also going to talk about a little bit about the IO access, especially when we talk about the remote disaggregated storage. So let's begin with a short high-level overview of inference. And I'm particularly going to focus on transformer-based inference workloads because these are the foundational architecture behind nearly all the state-of-art models like GPT, Llama. And let's start with a simple example, right? So a user sends a prompt, something like it's tomato, a fruit, right? And then the inference engine generates like n tokens at a time, right? So during this process, we have two phases. The first phase called prefill, and the second phase called decode. So during the prefill phase, your LLM engine or your inference engine receives the entire prompt, and then it generates the first token, right? And during here what's happening is the inference engine takes the input, tokenize them, map them to a vector space so the model can understand, and then the first token is generated. So at the beginning, because we know the entire context at once, right, this phase benefit of processing the entire prompt in parallel. So after this phase is finished, then the decode phase starts. So the decode phase is autoregressive, which means the texts are generated in a sequence once at a time, right? So what's happening after you generate the yes, you feed that first output token along with your prompt to the next iteration. It generates the next token, and then the next token along with the previous tokens fed back into your LLM engine, and then this process is continuous until you generate the desired number of tokens or the stopping criteria is met. So if you a little bit like go deep and look at, okay, what's happening inside here, right? So we have, inside the LLMs, we have transformer layers, right? There's a bunch of transformer layers. And in here, you have and in each transformer layer, you have a self-attention module and you have an FFN module, right? And the transformer-based models compute the relationship between all the tokens. So here, I'm not going to go to details, but what's happening is you have like three vectors, K, V, and Q vectors, and your model computes the dot product of the query vector of the current token with the key vectors of all the previous tokens. So this way we can tell how much the current token should pay attention to the previous tokens. And then you calculate the attention score, and this score is used for used to weight the corresponding value V vectors of the previous tokens. So here, during this self-attention, there's a lot of like recomputation happening. You have to calculate this K and V vector over and over again. So the KV cache comes as an optimization approach here. Basically, rather than like recomputing these K and V vectors, can we cache them in the storage so we can just reuse those cached K and V vectors rather than doing the computation. So this obviously like reduced the redundant computation time. So if we now go back to our first example, what's happening during the prefill phase, you take the input, process it, and you build the KV cache. So during the prefill process, actually the majority of your time is spent for building this KV cache. And then, then you pass these the tokens to the next iteration, and these like next iteration during the decode read the KV cache and also add more key and value vectors of this KV cache. So here, prefill phase is very compute bundled process, right? Because you spend the time for building this KV, and the decode phase is a memory bundling test. And there are like two parameters I want to talk about. Maybe you hear a lot these around like. These metrics, performance metrics are, the first one is the time to first token, TTFD. This is basically the time you send the token until your first token is generated. And this is basically when we talk about KV cache offloading becomes the key metric. And there's also like inter-token latency, which basically how long does it take to generate the next tokens during the decode phase. So if you look at today's large-scale inference deployments, we are going to see these deployments rely in disaggregated architecture. And the primary reason of that is basically because you have a different bottlenecks between prefill and decode. So by separating these two stages, you can improve the CPU utilization, and you can optimize these two stages separately. So today, when we look at these deployments, what you're going to see is there's a dedicated pool of GPUs or maybe nodes dedicated for prefill and similar to the decodes. So what's happening is your request is hits some like API server, and there's a router, and this router typically forward your request to one of those prefill nodes or prefill GPUs, and then this node is generate the KV, generate the first token, and then pass those information to the decode node, and then the decode node creates the output and then responds to client. So when we look at the architecture today, we see a lot of focus around the KV-centric architecture. This means there are like few routers out there, they're KV cache aware. So they know where these KV cache are located. So based on that information, they forward your request. For instance, if you look at Dynamo KV router, right, it's aware of where which data reside on KV, so it can prioritize or route the request based on that. Another example is from Mooncake, right? Those we see much more focus both in the industry and academia also to look at that. So okay, there's a value for KV cache, but like the KV cache is there, but why we actually need it, like, or do we really need it, right? So especially I'm going to talk about from storage perspective here. So KV cache computation is very expensive. For instance, we run a simple experiment here I want to share with you. So we have like the Dell server, XE9680. We run the Llama model. This model is a mixture of experts. So there's actually, even though there's like 400 billion parameters, there's only 128 experts, and each expert has only 17 billion active parameters. And this model, the windows can extend up until to 1 million token, right? So in this figure, you see the TTFD time on the y-axis, and we vary the context input sequence length on the x-axis from like 1,000 to 1 million. So the blue line shows here the growth of TTFD, time to first token. And again, the majority of time you spend here is for KV cache, building the KV cache, right? And if you map this curve to a trend, you're going to see very close to quadratic time complexity. And I also like kind of show you the linear growth, right? If the computation is not quadratic but linear, where the TTFD is gonna fall, right? So if you are doing a full attention computation, so if all layers doing full attention, then the complexity of KV cache grow quadratically. That's where the storage kind of becomes a play. All right, if we store that in some medium, right? Could be HBM, could be CPU, could be remote storage, then we will have a linear read time, right? So this linear read time can actually reduce that complex, quadratic complexity. However, I want to point out one more thing. So there's a lot of ongoing work today happening in both academia and industry, and these works focus on reducing the KV cache complexity and compute complexity and memory complexity. So we have techniques like sliding window of attention or chunk attention. These are actually not applying full attention to entire token space, but they're using subset of the tokens. So they reduce the both complexity of compute and memory. We have sparse attention, right? Like they just identify the important tokens, so only do the calculation on those. So this is a very hot topic, and we are going to see probably a lot of innovation in this space. So kind of what I'm trying to say is this like expensive compute become less and less with the newer model, even though their parameter sizes are increasing. From users' perspective, okay, who is going to benefit from the KV cache? What are the real use cases? So the value of KV cache become important, especially if you have a longer context, and that context take majority of the time of your the entire process time, right? And an example here is multi-turn conversation, right? Every time you ask a question, the model needs to consider the previous history, right? And as your dialogue improves, the history you build the history, it's become larger and larger. Another one is document summarization, right? Like maybe I don't know, you have a bunch of like papers, you want to like analyze them, ask a question, code analysis. You have logs, you have a bunch of codes, your engineer's going to look at them. RAG is another use case, and multimodal, right? Like these are dealing with like high pixels, like very large input data. So especially for those use cases, there's a lot of value for caching the KV cache. So let's look at a little bit about the capacity requirements of the KV cache. Again, this is very much depends on your model. The KV cache sizes depends on the model. And this is a very simple formula, like we can say is per token you have two values, K and V, and for each values you have to look at the number of layers, number of KV heads, dimensions, and precisions, right? So, and I want to kind of give you a sense to you what is that size going to be look like from storage perspective. So here, we are just going to considering a single session. One user just sent a request, right? So you see the model, these are using FP16 for KV cache. So we have Qwen, Llama 70 billion, and Llama 400 billion, right? So for one KV, for one token's KV, as you can see here, for instance, for Llama 70 is 330 kilobyte, right? So the range here is somewhere around tens of kilobytes, right? However, when you scale the number of tokens from like 1,000 to 1 million, and I know like these models doesn't support 1 million, but just an example, right? You're gonna see the KV cache linearly increase with your context length size, right? So, and in here, when we increase the token size, like input token size, you're gonna see we reach very easily the kilobytes. Okay, now if we go one level above, all right, I'm not just going to serve one user in my inference. Now I'm going to serve 1,000 users, 100 users, 10,000 users. Now, as you can see here, like I just took the Llama model here with 10,000 tokens or 100,000 tokens. And if we scale the number of users from 1 to 10,000, you can see very easily the capacity of the KV cache can scale around 2 terabytes, right? So that's actually where becoming a challenge to how to store this KV, how to maintain this KV cache. So if you look at today's architectures, LLM infrastructure, you're going to see two tiers of design. So the first tier, which is the GPU, obviously, right? This is the core, which store the KV cache. And here, you have somewhere around 100 gigabyte of capacity, right? With terabyte per second read speed, right? So I just also want to mention, not all the capacity on GPUs are obviously allocated for KV cache. You have to keep the model-based, right? So I know like the size of the memories are getting increasing, but the question is it enough? The second tier is some inference engines have a built-in support. They do CPU offloading, right? Here, CPU provides you terabytes capacity, gigabyte per second read speed, and you can share this CPU cache across multiple GPUs, right? However, all these GPU memory and CPU memory has still like some limitations here. And this limitation is obviously the capacity, right? So you will have a limited capacity, and existing systems today is using like external like connectors to extend that capacity. So do we really need extended storage capacity? Do we really need remote storage or local drives, right? So there's a paper, Mooncake, that's kind of give you why you need remote storage. So here, what they do is they did a quantitative analysis of cache capacity considering the Llama 17 billion model, right? So here, per token for KV cache is 230 kilobyte, and if you have 1 terabyte of DRAM capacity, you can hold 3 million token, right? And they look at 3 traces. They look at conversational traces, tool and agentic workloads, and they also have another publicly available traces which they synthesize. And these traces are publicly available, you can look at it, right? So on the graph, you're gonna see cache hit ratio on the Y and the capacity on the X, right? So if you look at that middle line, I don't know, you can see it with the circle. So that's where your local cache capacity with 3 million tokens, right? So when you look at this figure, you're gonna see that 3 million local cache capacity is not gonna enough to satisfy 50% theoretical maximum hit rate of these workloads. So it's fall behind. So this analysis suggests that, especially if you are running like a large inference, bunch of requests happening at the same time, right? Your like KV cache size is much higher, and to satisfy like certain hit ratios, like something like around 50%, you need larger capacity basically. So this suggests us, okay, now there's a value, and why we want to think about not local drives but shared storage, right? So one thing, right, today is like if you look at the production, they like operate at massive scale, right? They handle billions of tokens per day, right? And there's like a lot of dynamic sessions coming and going, right? Coming and going. So in these obviously scenarios, your local cache or your HBM will not be enough. So the remote storage provides a couple things, right? First of all, it's going to provide you from a like exabyte, maybe larger capacity, right? Your one session, again, can fit in a storage, but when you have a lot of like session happening, it will not fit, right? If you look at DeepSeek, for instance, right, they have 16 billion input per day they process, and they benefit from this cache. They are using this cache to have 50% hit ratios. So offloading allows, you basically scaling beyond the memory layers. And the shared storage also for KV also allow you to have cross-node access, right? So for instance, maybe you have GPU server 1 processing some data, GPU generating some KV cache, GPU server 2 generating some, maybe similar, maybe there's some reuse happening there, KV cache. So this way, first of all, you don't have to redundantly replicate this data. You can use the storage much efficiently, and you can also allow the sharing. And another, I think, most important part is you can have the session persistence, right? Like now you can pause it, you can migrate things, you can resume it. Like as a user, I can extend the time of my history or context window, right? Maybe I'm coming, asking question, and going 2 hours after I'm coming back. That KV cache can just offload to the storage and then can bring it back, right? So there are, a lot of like benefits. So I think in summary, what I'm trying to say is the shared storage is not a nice to have thing. It's a necessity if you want to support scalable, large scale LLM inference in the production. So there is also a recent benchmark numbers coming from SGLang that highlight the advantage of hierarchical caching includes the remote storage. So here they look at 3 use cases. They look at the GPU only use case, they look at the GPU plus CPU use case, and they also look at GPU, CPU plus storage use cases. So what they do is they run this on 8 H800 GPUs, they run the model QN3, 235 billion parameters, and they run a multi-term benchmark, they have it. So on the the left graph, you see the average TTFT time for these different three use cases. And you can see the time, you can see the time, and the y-axis, you can see the number of rounds of your conversation, right? So the more like conversations growing, you can see the benefit of having the KV cache store on the remote storage, basically. So on the reason is that obviously after certain rounds, your cache become full, so you start evicting it, or you're not hitting the cache, basically. So when you have a remote storage, like remote storage, your hit ratios increase significantly. For instance, like if you look at this like green line, you can see like CPU memory can keep up, for instance, until I think 70% cache hit ratio here with the yellow, but after that, it cannot keep up it cannot provide you high hit ratio. So that's why your TTFD start increasing. Obviously here in the setup, they do some optimization, they do prefetching, for instance, like once they try to prefetch the cache as well to eliminate some bottlenecks, but this is definitely like showing us the value of having a disk-based KV storage. So now the big question is, okay, what are the performance requirements for KV cache? Like how much, what is the trade-off? So here we have actually a trade-off, right? The trade-off is, should I have to compute it all the time, or should I have to read it from storage, right? And then, as I mentioned before, the compute time for KV cache is quadratic, right? It's increased with your number of tokens. And however, when you read this data from like any storage medium, right, it's gonna be a linear, right? So this creates a performance crossover point, right? A sweet spot. And beyond that sweet spot, it's always, or at least most of the cases, it's going to be beneficial to read that data from the KV cache, right? So this sweet spot, unfortunately, is difficult to say. Where is it? Because it's going to depend on how fast is your GPUs, how fast is your read, throughput. What is like the KV cache data you are trying to bring, basically. But, and there isn't much literature I found out there, but if you look at, for instance, DeepSeek, again, 3FS, they show the average mean bandwidth requirements for one of their servers was somewhere around few gigabytes. However, some GPU clients, they hit like 40 gigabyte per second read ratios. And in our analysis at Dell, what we see is after a few thousand tokens, you see the benefit of reading the data from the from the remote storage, some NVMe-based storage, basically. And if your storage can provide like few gigabytes burst read throughput, then you're gonna see the benefits. So now I want to like a little bit talk about what is the AI stack looks like and how you can do actual storage offloading today. So at the top, we have application layer. At the bottom, we have storage, right? And everything you see in the middle, the blue boxes are your inference engines. And inference engines, like inference frameworks, like have a bunch of components. At the top, we see orchestration layer, NVIDIA's Dynamo, LLMD, AI bricks. So these are deploy and manage the LLMs in the multi-node distributed environments. So they handle to allocate GPU resources, routing the requests. They typically run in Kubernetes, not all the time. And they try to scale horizontally. Then each of these orchestration layers has to use an inference engine. So this is VLLM, SGLang, TensorRT, right? These are optimized to run a single model instance. So they have a built-in like batching, memory management things. All these engines have a built-in local KV cache memory, and some of them only support GPU, some of them support both GPU and CPU offloading, but by default, none of them today support remote storage offloading. And when I say remote storage, like file protocol, object protocol, those I'm talking about. And then there's like another software stack called KV cache layer. This is for offloading the KV. Here we're gonna see LM cache, you're gonna see Mooncake, Dynamo KV block manager is another one. And the goal of this layer is provide a globally managed multi-tier cache for the upper layer LLM inference engine. And then we also have a cache, the libraries that these KV cache layer use called transfer library. The Dynamo Nixel is one of them. Mooncake transfer engine is another one, and the goal of these transfer libraries are to enable fast and low data movement between given two data points. This could be between GPU to GPU, GPU to CPU, or your storage, right? So if you look at the cache management and tiering, so we have the inference engine at the top, something like VLLM and SGLang. These have, as I mentioned, have two-tier or maybe single-tier, and they have their own local cache management. So they either use some type of like prefix tree, right? And they store the KVs in block granularity. So it's not just one token KVs they store. They basically pack multiple like tokens together, KV values of the tokens together, and that's their like cache. How to say, like, that's how, what is their like granularity when they manage the cache. They also provide like abstraction classes. You can, there's like really good description. You can just implement your own remote storage uploading techniques. So now if you look at the bottom layer, and I just give an example here, LM cache, but Mooncake is also similar. So they have provide the tier architecture, but their cache management is separate than the one at the top, right? So there's gonna be two different cache management happening here. So for VLLM and SGLang, whatever the data is generated at above layer is going to be written automatically to the LM cache. So VLLM follow write through. So basically, any data you generate is automatically written to the LM cache. SGLang is a little bit more flexible. You can do selective write through. You can do write back. But it's not going to be like the evicted cache is not going to be written to the LM cache. So you're either going to like whatever generated on your HBM or like upper layer cache is either going to be written or not. And they have their own eviction. They use LRU, LFU, FIFO, right? And again, these also operate on block level granularity. However, their block sizes are much larger than the actual VLLM. So in VLLM, for instance, your block size is 16 tokens. However, these like the storage offloading engines like use larger blocks to make sure they can like improve the I/O throughput when they read or write from the storage, right? For instance, the VLLM use 256, and if you run Llama 70, use the LM cache, per file for KV cache generated is somewhere around 32 megabytes. So it's much larger granularity we are talking. Again, this is a configuration. You can just decide to store, okay, I'm just gonna store one token KV. That's my block granularity. You can do that, but today, at least what I see, to have a better like storage throughput, I see much like larger blocks adoption basically, and all of them obviously support zero copy, KV cache transfer, and some of them like LM cache also have some optimization about like compression. So they compress the KV cache, and during the decode, they decode that using the CUDA libraries, basically. So if you look at, there are like a lot of options here. It's not just one storage is there available for KV cache today, right? We have VLLM, SGLang, right? We have KV cache managers, Dynamo, KV block manager, LM cache, and Mooncake. And for all of them, when I look at them, they're like trying to support upper like VLLM and SGLang. So there's like, for instance, today I believe Dynamo doesn't support SGLang, but it's in their roadmap, right? Like it's getting there. And then we have the transfer engines, two popular transfer engine here, Nixel and Mooncake transfer engine. And then we have the protocol level. As you see here, there are a lot of options. You can write the data using RDMA, like GPU direct storage, right? You can use POSIX. We see now, for instance, even S3 there. Like LM cache has a S3 support. Nixel has a S3 support. They support KV stores like Redis. They support block like NVMe over Fabric and CXL. So the options are there. I mean, obviously performance is very important, but you can use any storage backend today with the existing stuff to offload your KV. So finally, I want to like talk about the storage access pattern a little bit. So here is, first of all, KV cache workloads are read dominant, right? You generate the KV once, but you sometimes read them multiple times, basically. And then the reads are, like if it's a miss on the CPU or GPU, then you read the data, I think there's a typo here in my slide, but you read the data from storage, right? And you have to be an exact prefix match. So what is the read size? Again, as I mentioned, read size are fixed. Every block that you read is same size, somewhere around kilobytes and megabytes. And the read pattern is you cannot access a particular token's key and value within a block. You either read the entire block and bring it, or not. So it's sequential access within the block for the entire block. However, you can obviously randomly access different blocks. So similarly, right now the writes are not like written as like, okay, I'm going to evict the data from my GPU and write, or CPU cache to write the storage. It's automatically going to replicate it at the underlying layer. Similar to the reads, you are using a fixed size blocks. And one thing to say is there's no modification. You write the data once, and you don't overwrite it, basically. So access granularity is block level. And I think the most important thing here is your inference is very latency sensitive. So it's not like, I think, maybe it's not like a training. You can like prefetch some data beforehand. So latency or throughput oriented. So the latency is really, really critical here, right? So you want to, like, when you talk about KV cache, we want to talk about, like, you want to consider RDMA seriously. Especially this is more critical on reads, because reads are on the critical path. For writes, what I believe, at least this is what I see, it's beneficial, but it's not as critical as the reads. And the main reason is because you generate your KV cache, and you can always write that at the background asynchronously. It doesn't have to be written immediately, but that's not the case for the reads. So, and if you look at the current libraries, even with like the GDS kind of stuff, still the I/O is initiated using CPUs, right? But basically, that's the current status I can tell you about the remote storage. So just to summarize, I hope I will convince you there's like the value of really having a shared storage. As I mentioned before, especially I think the value is become more critical when you have like large scale, right? The shared storage allows your inference engine to scale much more. You can support much more concurrent requests at the same time, right? And then I think that's all that I have today. Thanks again, and happy if you have any questions. But yeah.
On slide number 18, if you can go there.
Yeah.
I don't see, my understanding from storage point of view, block would be very performant.
Correct.
But I see that in the LM cache, if you look at the solid lines, you don't have a solid line to block. And the KV connectors that are built are either for POSIX, S3, or KV type or file type interfaces, but not block. Is there a reason for that?
It is actually supporting block. So the question is, the LM cache doesn't support block, and is it just for file and object? So LM cache supports block through Mooncake. So if you look Mooncake, if you follow the Mooncake, like it's going to the Mooncake, and then Mooncake transfer engine to the block. So it's still supporting it, but they just like use the Mooncake software to do that.
That's the exact question. Mm-hmm. For example, if I want to build a block connector, I would have to build it in Nixo rather than in VLLM directly, for example. Why is that?
So the thing is, I think, first of all, there's no focus in the VLLM community itself to do storage offloading. They are focused more on how I can improve the compute side. That's one thing. So storage offloading is a little bit happening today, either something like LM cache, it's a separate community, but they're really like working together, or you are a storage provider yourself, you can implement your own. But from the inference community, their main focus right now is on how I can improve the compute, make it better, rather than doing the storage offloading. That's one reason. So what I see is initially actually Dynamo KV was separate, LM cache was separate, like it wasn't using the Nixel or Mooncake. Like Nixel integration with LM cache happened recently, like maybe a week ago or 10 days ago. But what I see is I think everyone's gonna make sure their software is like support all different software stacks. Because today I think there's not one software stack that dominates. I mean, there's still few, but still it's very evolving. It's changing. Like every week there's new changes there. So I believe like these communities from like industry like NVIDIA, when they build Nixel, they want to support other software because maybe some of their customers gonna use that, right? So that's why I think we see a lot of like kind of different softwares, but somehow they also support each other. Hopefully we're gonna see more like one or two of them becoming more, I have to say, like state of art, but it's not there right now. Yeah.
You mentioned GDS is still not supported. I assume that what you meant is CPU still initiate the I/O, but is it still moving data directly to GPU memory?
Yeah, it is, the question is, yes, it's still, you are bypassing the CPU bounce buffer. You are doing the GPU direct search.
By default done by most of these providers, I also, at least from a different source, I also had this argument on the fact that if you're actually providing a layered cache, a hierarchical cache, sometimes it makes sense to move it into CPU memory because it's a lower tier of your cache and it's higher in capacity and can be shared across GPUs on that. That's one argument for not doing GDS. So, do you know what these providers do?
So if you use LM cache actually you can provide GPU plus storage tier, and it can prefetch the data from storage to the CPU. So there's that functionality. This way, in that case, obviously, you're going to read from GPU to HBM. But they also provide options, like you can just have, I'm not going to do CPU, I'm just going to do storage cache layer, and I just want to do GDS and bypass the bounce buffer. So I think there's value of, like, I think it's a little bit depends on what is your access pattern. If you predict what's going to hit, if you can prefetch that to the CPU memory, then that's better because CPU is going to provide you better bandwidth, right? However, if you cannot predict that, then you're going to hit the bounce buffer issue. So yeah, it's not easy without to see a lot of, I think, traces. And for the GDS part, some of the GDS implementation to these like softwares like LM cache actually developed by industry, like some companies, storage companies. But some of them, the community itself developed because there's a need or there's a requirement for that. So it's kind of a mix. Yeah. Yes.
So what is the eviction policy?
Eviction policy? Yeah. Okay, so the question is, what is the eviction policy? So in the LM cache, when you go to the storage offloading, Inference engine doesn't manage that cache. And today, they just use LRU, LFU, that's it. They have no sense of what is that block belongs within the larger context of your history, right? If you look at VLLM and SGLang, their cache manager, they actually use a prefix cache, prefix-based cache. So which means is you know the blocks where they stand on your entire conversation. And when they do the eviction, they build a tree and they're trying to evict from leaves because leaves has less sharing. So when you move to the top of the tree, you will have more sharing happening. So that's the eviction policy of VLLM and SGLang. However, when you offload them to storage, it's still, I think, an optimization opportunity. So they're not looking at that. Yeah. Maybe there is, but I'm not aware. The question is there any comparison between swap memory and VLLM standard compute, right? You are asking. I believe there is, but it's not on. I can just follow up offline. It's not like I don't have the numbers to tell that. Yeah. Yes. Yes. So the question is, if the block size of LM, like the storage offloadings, are larger than the available, the one that used on the the inference engine. So when you read something large block, is this cause pollution of the memory? If I remember correctly, and I need to double check, I believe that's the case. I hope I'm not mistakenly. I need to double check. That's my understanding. Yeah.
So what is the typical time to live something in a KV cache? It's a two-part question. Typical time to live, and is there any benefit to data protection? Or can the cache just be thrown away and easily rebuilt?
Question is, what is time to live? And is there a value of, what was it? Data protection. Okay. So there's definitely one paper that looks at time to live, and I don't remember it right now. I'll need to follow up offline. And I don't even remember the granularity. I probably didn't read the paper carefully, but I can comment. But for the, so the KV cache today treated as this is, you can lose it, right? You can recompute it. So one thing I think I'm also not trying to understand, is that the case? Are there any value of maintaining the KV cache, right? That's the case for checkpointing before, right? Everybody think when we look at the training, you don't have to keep the checkpointing after your training done, but that's not the case. There's some contextual value of it, right? Like, is this the case for KV cache? Today, what I see is no one's looking at that question, because the question here is like how fast I can bring the KV cache. No one's looking at, is there a value of metadata? That's, for instance, is there a value of storing them on S3 maybe, right? What is the life cycle of that KV cache? So those are, unfortunately, I don't have an answer. I don't see much focus on that. But I think, based on what I see on the training happening, I think there's going to be a value of like maintaining those KV caches in longer term, especially when we move towards the agentic workloads. Things become more deterministic, right? Like when you as a user, you ask a question, I ask a question, there's no sharing. However, when we switch to agentic, then things become more deterministic. Maybe the agent's going to say same prompt, same question. So then there's going to be a value of maintaining that KV cache. Maybe you don't want to lose that KV cache, even though if you want to recompute again, right? I think that's at least what I think things going to evolve. Question. Yes.
So you were talking about compressing the KV cache. So what's your trade-off when you say that?
I didn't hear you. Can you say again?
So you were talking about compressing the KV cache.
Complexity? Compressing the KV cache, yeah.
Are there any trade-offs with that approach?
So, I have any more slides? So, in the compression, the cache gen, this is a paper. I think they didn't reduce the accuracy, and they improved the performance up to 3 or 4 times, if I remember correctly. So. This is not a default mode, but a lot of people actually, when they use LM cache, using it because of that. And I believe the reason why compression actually works, and they do very smart compression, by the way. They do layer-based compression. They apply different compressions for different layers and based on the importance of the token. So when you look at the KV cache, you're going to see a lot of sparsity in certain use cases, which means only subsets of tokens actually carry the values. So we see a lot of like pruning, quantization, compression, similar to I think what we're observing checkpointing in training. So this is a little bit like I see apply the KV cache. Yeah. Yeah.
But for some of the workloads, it might be not necessary that you get
Yeah.
right there. Something that's estimated that is much more. Especially you mentioned agentic workloads.
Yeah.
So would you agree that it might be beneficial to keep those workloads high and just devote the GPU capacity to the workload that's really executed in real time?
Can you repeat the last part? To keep the TTFD high and?
And then use the cycles that you get from the GPUs that are available for other workloads.
Yeah. I think that's probably the right approach, right? Every applications have different SLA, so if you're always trying to optimize it to improve, to reduce the TTFD, then you're gonna waste some of the cycles because, as you mentioned, some workloads can tolerate that, right? So you can, I think, I mean, I haven't seen that today apply in the large inference, but I think for large inference with bunch of requests coming, I think that SLA has to be careful. Look at carefully. Scheduling, along with KV cache, like storing the data in KV or not, reading from storage versus compute, should be considered. But it's, I think, a very big problem, like space.
And in this case, S3, for example, can be already viable because you don't know it takes a lot of time to load data from S3 to the data. So the second question, fun question, I wonder, based on your research so far, can you make a guess? Let's say I buy a GPU cluster without offloading under GPU, and now I introduce the caching, KV caching, storage, sharing. How much less GPUs can I buy? Can I buy 80 instead of 100 because now I cache KV? Or can you make just a prediction? Or
So, simple math. So you have 100 GPUs, and I hope I'm gonna do the math correct. And you have a KV cache, and your KV, if you read it from storage, you increase I'm just making up the numbers, 10 times, right, your TTFD. Again, I'm looking at TTFD here. Then you can say, okay, I can serve that many users 10 times faster, which means I can just buy 1/10 of the GPUs, right? Maybe this is not the correct math, I don't know, but that's how I would think right now. But I think it's interesting to look at from how much, how much reduction I can have with, as you give an example, like if I have 100 cluster, assuming some uniform access to that cluster, how much reductions gonna I have from the cost? Yeah. Sorry.
To kind of build on this question, do you see the floor on the number of tokens in a block that is reasonable? Like, how small can that reasonably get? There's a lot of pressure for it to get bigger. As context points are getting longer, Barista is getting longer, and we talk about let's say 4,000 tokens, that block size of 256 down in the lowest layer is still pretty small, right?
Yeah.
See that getting smaller?
So maybe, I mean, it can get, I think I don't have the right, I don't know, it can get smaller. But one thing, SGLang has support both token level caching and block level caching. So they're, one of the optimization they have is they can build the tree based on tokens, so they can have more sharing, like partial sharing. So, and for instance, from SGLang perspective, if they want to manage in the future the storage as well, are they going to prefer that or not? But I think when I look at storage parties, because of the larger I/O, you can bring them much faster with less overhead. That's what I see people tend to go, larger I/O, larger block sizes and I/O. I didn't see the opposites so far. Yeah. Yeah.
In line with what was said. So, different context though. So you mentioned you want to pack multiple tokens into a larger block from optimizing storage point of view. Is there locality with respect to users, sessions within this,
Yeah.
the same user packed together? Is that also done?
So there is definitely locality within the KV cache share, like how much KV cache shared within one session and across sessions. Within one session, especially for multi-turn conversation, there are like publications say 50, 70%. For a cross session, I don't have any like data to say like here it is.
Specifically within a session, for this user, if I read this 1 byte worth of block from the storage, most of it belongs to this user. Is there any that
Yeah.
Other question is, you mentioned zero copy here. Is that in what context? It's like avoiding the
Bounce buffer, yeah, avoiding the bounce buffer, yeah. Okay, my time is up. Thank you very much. Happy to talk offline. Thank you.